In this lesson, we are going to be looking at a question where we'll be using areas and the fundamental theorem to solve our integral. So each and every time you see your width like your areas, then you know you're going to be working on a Cartesian plane. But if you see your fundamental theorem, then you know that you're going to be using your what? You're going to be using your antiderivative. So all these two methods, they should be giving you the same answer. So if they tell you to do your area, you can do your quick calculations and get your final answer. Then to confirm, you can use this fundamental theorem to check if indeed you're still getting the same answer. Then with your fundamental theorem, you will always be given a formula that looks like this. You'll be given an integral that is between your region A and B. Then they will tell you have your f of x and you have your dx. This is the same as equals to your f of x. Then now we are going to be finding this between your b and a. You always write your b at the top, then you have your a. Then this is the same as having your f of b minus your f of a. So you will see also in your what's this thing, your definition, they would say let f, which is this smaller f that you see, be continuous function on the closed interval, which is going to be in between a and b. See, so that one, the smaller f, is going to be a continuous function in this region a and b. So now they say let f, which is the bigger one, this be an antiderivative of f, which is this smaller one. Then what are we going to have? It means now the derivative for the bigger f is going to be equals to your smaller f. But this will just make much sense when we are doing this calculation, that you get the derivative of the bigger f being equals to that smaller f on what? On the same interval, which is going to be your a and b. So okay, let's continue with the question, then I'll get back to this part on a later stage. So as I said, when you see the words areas and this one, you go and analyze this one, that okay, in terms of this one, I have my 5 and 1. So if you're comparing it to this here, it means here you're going to be having your b and here you're going to be having your a. This exactly the region where you're going to be working within your graph. So what does this mean? It specifically means within your graph you're going to be working exactly between 1 and 5. So those are the x values that you're going to be having. So it's going to be between 1 to 5. Then the second one that you check the type of function that you are given here. You see you have your 6x here. What's your 6x? This is your linear function. And this being a linear function, what type of a linear function it is? It's a positive linear function. It means it's going to be having a slope that is going up since it's positive. So we're going to use all that information that we know to be able to do our Cartesian plane. So we come to a Cartesian plane and say, okay, we have the region between 1 to 5. So we can come and say we have that 1, we have that 2, we have that 3, we have that 4, then we have that 5 here. So now we have to check. Remember, in order for us, we are given a function that is 6x. in order to find the y values, we just have to input these x values into this one. So it meaning you're going to have 6 multiplied by 1, and this will give you 6. 6 multiplied by 2, this will give us 12. 6 multiplied by 3, this will give us I think it's 18. Then 6 by 4, this is 24. Then 6 by 5, this will give us 30. So this helps us in such a way that we can use multiples of 10/10 in the y-axis. So we now here we can just say here we have 10, here we'll say we have 20, then here we'll say we have 30. So when we are having 1, what are we getting? When we are having 1, we are getting 6. So 6 will say it's somewhere here. Then when we are having 2, we are getting 12. 12 will say it's somewhere there. Then when we are getting 3, we get 18. 18 we can say it's somewhere there. It's somewhere there. Then when we are getting 4, we get 24. 24 we can say it's somewhere there. Then when we're getting 5, we're getting 30. Let me just do it like this, that I can be able to reference. So we're getting a 30, 30 is there. So what I also like to do is that, you see the last ones that we're having 1 and 5. I just like to draw vertical lines that will look like this. Then now we can be able to plot that, okay, this would be like a straight line if you do it properly. So now since I have something like this, and you see that now, okay, you have to work this area of this shape that you have here. So you kind of notice that it's going to be difficult if I'm working out an area of something that looks like that. But if you look at it in this way, that okay, I'm going to complete it for you, that okay, it's going to be like this. You have it like this. But now if you cut this into 2 and say you have something that looks like this, remember here, that's exactly where you have that 6 between here 2 there. So it means from here to here it is 30, but from here to here it's that 6 that we had here. Then it means we can say we have this height for this one, it will be 30 minus 6, which is going to be 24. See, so now we can work this ones separately. We can say we have this shape at the bottom, and we also have another shape for the triangle at the top. So if we are going to consider these ones separately, we have to determine the area for this one, and we also have to determine the area for that one. The area for a triangle, it's half base times height. Then for this one, it's going to be your length times breadth. Then we go and check that, okay, what is our base? Our base, it's the bottom part from here to here. So how you would find your base, you have your 5 and you have your 1 this side. It's your 5 minus 1, then you get your 4. So you have your half, then your base is going to be 4. As I said, it's just merely your 5 minus 1, then it gives you 4. Then what's the height for this at the top? Remember, this is sitting at the top. It means I'm going to be taking my height from here to there. I've already explained that part, which now it's going to be that 24. Then come to the bottom part. What do we have? We have the length, which is the longer side. It's from here to there, which is 4. 5 minus 1, then you get your 4 multiplied by the breadth, which is your 6. Then this gives you how much you have your 6 by 4, which gives you your 24. See, then you have half of 4, then this gives you 2 multiplied by 24, then this is the same as having your 48. You see, then now we will say the total area that we will have equals to the area for the triangle plus the area for that square shape. You see, so now we have that one, which is your 48 plus your 24. Then this 48 plus your 24, I think it gives you 72. It gives you your 72. Then that's the method where you have to use your area. So now suppose that we are supposed to use this one, which is our fundamental theorem. So I just hope that the first method was clear and understandable. Remember, what did we have to do? We checked the region by checking our integral that we have 1 and 5. Hence, that's why you see I started with 1, then ended up with 5. Then the second one, what did I check? I checked the function that I have here. I have my 6x, which is a linear. Then to determine the values that I got here, the corresponding y values, I know I have 6x. Where I see x, I input my 1, my 2, 3, 4. Then it's just going to give me those numbers that will be able to help me draw a graph. So, but I still had a problem because I had an irregular shape. So when I had an irregular shape, I just had to cut it here so that I can be able to work with this shape at the bottom, a square one, and a triangle, which is what I did. Then I considered the area for this one and this one. Then I calculated everything. Then the base, you always work it in this way, because it's just easy to make a mistake that your base is 5. You see, it's just easy to just say it's 5, and if you count it nicely, you'll see that okay, you have 1, 2, 3, 4, which is why here I got my 4. Or you can just always take this last number and deduct the first one that you have, your 5 minus 1, then it's going to give you your 4, as you see as your base. Your height, I took the height for this one, not the height from the ground, because this triangle is sitting on top of a square. Then for a square, I took this individual 6, which is the height from here to there. Then I added those two, then they gave me 72. So now we're going to go to a method where we're using the fundamental theorem. So your fundamental theorem, mainly you'll just have to use this formula together with your antiderivative knowledge. So you will see, if you know how to differentiate, then you will know how to do your antiderivative, because we know that the antiderivative of 6x is what? It's definitely your 3x squared. So how do I know that it's a 3x squared? I know that it's a 3x squared because if you can take this back or work this one back, you're still going to get back to your 6x. So let's just say now we were to differentiate our 3x squared. If we differentiate our 3x squared, we are going to get what? We are going to get this multiplied by that. We are going to get our 6x. But let's just say now you don't know how we go from here, the antiderivative. Remember, this one is your antiderivative. Oh yeah, okay. Nah, I'm making a mistake. Oh, the antiderivative is definitely this one. So what if now they give you a 6x and you don't know how they come to this antiderivative, but you do know how to differentiate your 3x squared to be your 6x. So now we're going to be looking at our 6x in order to arrive at this 3x squared that I had at the back of my mind. So now we will say, okay, we have an integral of 6x dx. Then we know that we can take this side, this 6 to the other side, and we'll have our 6, and we have this integral sign, then we have x dx. So since now we're only left with one term here, it means we can just focus on it in the meantime, then bring this back when we are done. So you know this one can be represented as your x to the exponent 1. And what do we know when we have this type of terms? We know that we can actually use our power rule. So what does our power rule look like? So we know each and every time you have something like this, the power rule always will say you have something like your n plus 1, then you have your x to the exponent, yeah, I think it's n plus 1, it's your n plus 1. So this is mainly the power rule that we're going to be using in this question in order to work out this x to the exponent 1. So if we're going to work this one out in terms of this power rule, what are we having? We will say we have, remember this 1 is taken as what? As n that you see here. So we're going to say we have 1 over 1 plus 1, 1 plus 1, because 1 here it's for the n and the other one is for from the formula. Then here we still have our x. Remember, this can change, can be t or any other random letter that you're going to have. Then here you still have your 1 plus your 1. Then this is the same as having 1 over 2 multiplied by x to the exponent 2. You see? So it means now the final answer here, you have your x to the exponent 2 over 2. Then remember, but we still have this 6 that you have on this other side. It means now you can transfer back this 6 this side. It will make we have 6 multiplied by x squared all over 2. Then your 6 divided by 2, the final answer will give you something like your 3x squared. So you see how we've managed to work this one backward to that one that we had. Because if you just meet someone, they just tell you you have your 6x, what is the antiderivative of 6x? If you've never done this once, you won't be able to know it unless you sit down and follow the rules. Then you'll be able to come back to this one. Then now if they quickly come again and ask you what is the derivative for your 3x squared, then you will know that it's 6x. You see how they're basically an inverse of one another. So now that we found that 3x squared, it means now we can use this fundamental theorem or formula that we have. How is that gonna look like? So we will say we have that fundamental theorem formula, then we're going to be working this in between the region of 5 and 1. Then we're going to be having that 3x squared. You see? Then you're going to be between 1 and 5. Then you will say you have your 3 into your 5 squared minus your 3 into your 1 squared. Then you have your 3 multiplied by your 25 minus your 3. Then this is the same as having your 75 minus your 3, then this gives you 72. You still remember the same, the first calculation that we did using a Cartesian plane, that we got 72. Then when we are coming to this one for the fundamental theorem, we are also getting 72. So mainly that's how you confirm that indeed you are doing the right calculations, by using your areas and your fundamental theorem. But they won't always ask you like this. They would rather ask you one at a time. So if they say you use areas, use a Cartesian plane. If they tell you that you do fundamental theorem, you will take your 6x like this, then work it out with your power rule to get your 3x squared. Then now you will have to work it out between 5 and 1. Remember here, that's how they tell you have to deduct the function of b from the function of a. That's mainly the proper way that we did it. Then we get 72 here, matching the 72. That's it. So it means now we've done our whole calculation proper. So yeah, I'll see you in the next video or next series, where we'll be calculating the areas of enclosed graphs. So see you in the next video.